So thank you very much for the invitation. I will be speaking in English since there are some people in the audience that are not Portuguese native speaking persons, so I will be doing this in English. But I think also the audience will follow me quite easily. So I'll be here today to talk mostly about Project Safefire, which is a project funded by FCT. So Project Safefire has the aim of following the in-depth technologies of sensing to help to assist firefighters in particular, but can also be used for other rescuers teams. So first, before talking about Safefire, I will give a bit of my background. So you can. Yes. So my background that I'll be mostly focusing here is in textile electronics. So textile electronics, as the name follows, is the electronics that is fully embedded in textile substrates. So for that, it uses mostly organic semiconductors or other type of inks, conductive inks and other materials that can be fully printed or used in processes that are textile compatible, like roll-to-roll processes, screen printing, graving, and these processes are very commonly used on the textile industry, and they have also been quite used in organic electronics, which is part of my background. So combining these two possibilities really allows to have fully in-depth electronic devices in textile fabrics, maintaining their flexibility, their stretchability, and also their conformability, and can also be used to doing scaling up using traditional textile manufacturing processes. So this is important because textile industry in Portugal is very relevant. Like 10% of exports in Portugal are from textile industry. 19% of workers in the industry are related with textile industry, and so there's a big relevance for Portuguese economy, and they need to create technology to innovation into this area to be able to be more competitive and also to add value to their products. So having this functionality of these sensors embedded into textiles, this allows to multiple of applications in health and well-being. So just having conductive textiles, for instance, they can be used as dry electrodes for monitoring the heart rate, the electrocardiogram, temperature, electromyogram. So these can be used for using an assist not only in fire workers but also in other type of health assistance. But it can also be used in embedded sensors to evaluate position and movement of human movement, and also to embed other type of functionalities of devices that can be used for fully embedded IoT devices. Also another advantage of using these type of materials is that they allow a more sustainable electronics, because they basically use materials that are not critical. They use processes that are used at low temperature, room temperature, not needing a clean room environment. This allows low cost processing and more cost-effective solutions, and with environmental impact, with lower environmental impact into the environment. So if you combine these sensors, embedded sensors, with other functionalities, like in particular the physiological computing approach, where you extract these biosignals that could be the heart rate, the electrocardiogram, the electromagnetic activity, and you use it in different type of variables. You can extract not only some health parameters, but also you can evaluate emotional stress, anxiety, other types of features that can be adequate to different type of applications. So these are some examples that were developed within the group. So this is a wheel that to allow to evaluate the stress for monitor the health status of drivers. And this is a T-shirt for also monitoring the electrocardiogram for here health for sports activity, but could also be for other types of activity. So
I'm sorry, we were having an issue with the screen sharing. For the people in remote, could somebody just please tell me in chat if you are now seeing slide number 4?
Yes, we are. Yes, we are.
Okay, thank you very much. There was an error in the screen sharing. Okay, thank you very much. Sorry for the interruption. And now we should be seeing slide number 5, correct? Yes.
Okay, so this is another example of another wearable device that we have developed. So this is a sock, which can be also, this has electrodynamical activity sensors. And then you can also have to monitor, there's a movie.
Oh. I'm going to try. Sorry, I have to press the actual play button.
Yes, yes. So you can track the movement, and you can also extract some signals, and the activity is also related with some parameters that can be used to evaluate, for instance, emotional stress, anxiety, and other type of parameters. This particular project was to evaluate, to monitor epilepsy and to epilepsy patients. So, what is the relation this with Project Safefire? So, one problem that is very critical in terms of decision in critical situations, in particular in emerging decisions, is there are problems in decision taking that do not take into account some human evaluation factors like the fatigue, the stress that firefighters are exposed. We also, not only the firefighters, but also the decision taking management teams. So they usually work for very long hours, sometimes in very critical situations, which are dangerous, and also creates additional stress factors, and this has an effect on their response in the ground that affects positive reaction and provokes many times a wrong decision in terms of emergency decisions, which affects and provokes some victims, also increase the problem or the fire extent because it was taken bad decisions, and this was not, and human factors were not sufficiently taken into consideration, and these were not taken because there is no tools that could bring this information for coordination teams, coordination supervisor to be able to respond and to provide answer to eventually move certain members that are not in good condition because he does not have information, and this affects the decision and the emergent decision, and sometimes with critical problems. So what are the objectives of Project Safefire? So basically we want to integrate human and ambient monitoring fully integrated into firefighter garments. These to increase the safety of fire workers and also to prevent dangerous situations and to monitor and tackle information that can be decisive for decision support. So the team involved in the project is, well, we are coordinating the project. This is an FCT project. So it also involves IT, and they are experts in signal analysis processing, particularly in biosignals analysis. ADAI, which is with Professor Xavier Viegas, which they are expert in firefighters management teams, and also in thermodynamics. So they can also evaluate the response of materials and the electronics in terms of inflammability, which is also important for the project. It also involves medical experts from the medical faculty of University of Coimbra, and we have textile company, Latino Group, which is their expertise is in firefighter garments and also technical workwear. So this is the team, and what is the problem with the many wearables that are trying to be put into firefighter garments? They mostly rely on conventional electronics, so either they use silicon-based devices which are rigid, they are not conformal to the body, they are extra weight, and they pose limitations in terms of wearability in this particular scenario, and they are not comfortable. Moreover, if you think in challenges that are related to the specificity of firefighters, is that they work equipment, they weigh 35 kilograms, and it's quite heavy, and it occupies a lot of space. This poses problems on where to put wearables, so they cannot be put they have limitations in terms of where to use them, because they have to be compatible with this equipment, and not only with this one, but also other types of equipment, like the hose, that can only, without water, weigh 12 kilos, and with water it goes up to 90 kilograms. So you cannot include extra difficulties for the movement of firefighters, so you have to create solutions, technical solutions that can be comfortable, can be wearable, and can be used in these conditions. So other problems that arise with the specificity of firefighters is that they are exposed up to temperatures of 300 degrees. So this means that, and also very harsh environment conditions, toxic gases, smoke, sun, very bright sun, and these also pose problems to the electronics that can be used in these conditions, and the materials and the electronics needs to be also be non-flammable, because this is a technical requirement for firefighter garments. So if you think on wearables, additional wearables, if you need to wash them, in the end you have other problems like this, and its washability, because if you want to have a fully embedded solution that is lightweight and completely embedded in your garments, then it also needs to survive washing, and this is another problem. So to address this problem, we in Safefire, in Safefire project, we decided to use an hybrid technology strategy. So we have the embedded sensors in a t-shirt, and with the part of the electronics, mostly the communication, the data processing setup, and also the battery involved in a detachable model that is also small, and usually it's connected in that part in the red circle, and so you can detach it to be washed, the t-shirt, for instance, and but it also allows the comfortability, and it's really very small weight. So the position of the electrodes were already studied, and they were positioned in places where not only they would not be interference, or will be less interference about the movements of the firefighters, but also other type of difficulties that usually have with the connection of electrodes in touch of the skin. It's with the hair pills. How do you say this in English? Hairs, yes, hairs. Body hair, like I remember, body hair, the place of the position to extract the best signal, and also the size, they were already considered, and so we decided that, we not decided, we evaluated that this position in particular was the best position. So for the sensors, what we can do with this model is we can measure in real time the linear acceleration, the electrocardiograph, the heart rate, we have accelerometer, so you can measure the position, and this can be tuned already in a mobile phone application, so it can be evaluated in real time, and you can record record also this data. So we did the first 5 field tests in Gestosa field tests. This is placed in Serra da Lousã. And the first, these were coordinated by our partner ADAI. So the first field test was last year in May. So this field test has to be done in very specific. You have a very short time frame to be done, because you need to have sufficiently high temperature to be close to summer temperatures, to be simulating the temperatures that the fires exist. But you cannot have extreme temperatures because or winds, because then this is usually also for testing and training of firefighters. So you have to have some control of the environmental conditions with these tests. This means that we have a very short time frame for doing these tests, and usually it's on May that occur. So these were done in May, in last May, and the first tests were a bit limited because we only had 1 prototype, so we have limited information, but we have identified some of the problems. One of them is that the acquisition was dependable of a mobile phone, and so firefighters cannot use mobile phones. And the range, the communication range of our application to the system was 8 meters. So this means that the position, because the firefighters, they have different positions, you see them online, but these are positions that they have to follow when they are attacking a fire, and so we could not get close to some of the positions and could only test some of them. So this poses some limitations, but also give us some information on how to improve the prototype. So we are following this testing, which was limited. We developed a new wearable firefighter prototype. This was already done in certified sweaters from our partner Latino. This means that technical garments for firefighters, they have to support, they cannot be flammable, and they have to support temperatures up to 300 degrees. They have to be also, when you do this washing test, which has to be done, they have to survive 100 times at 90 degrees Celsius washing cycles. So these are all certified. So we embedded our sensors. You see here the inside, below we have the inside figure of the sensors, and outside it looks like we only have, the part for the touchable, the communication part. So we also embedded in the detachable communication sensor model a temperature sensor, so we can acquire also body temperature. And instead of doing real-time communication, we put it as a standalone operation. So this means that we don't have to use, we can collect data. This is collected in a memory, and you don't have to use to have a mobile phone. So this allows us to have bigger liberty and to collect information from all the type of firefighters. And it also has a long-term data logger, so this means you can accumulate data for long periods of time. So this solution will help us in the next Gestosa field test, which will occur in May, to have not only more firefighters, but also we can have several we have now 10 prototypes that can be used in the field, all simultaneously, and this will allow us to get more data information from the firefighters. So to prepare this field test that is going to occur, we have already have a pool of 15-25 fighters, which they are being medical analyzed by our medical team, which is going to scrutinize if they have other medical conditions that could affect the analysis of the signal that we are going to extract. So this needs to be done because firefighters, unfortunately, are usually not very fit individuals, and actually they can have many hard medical problems. So this has to be done priorly to make sure that when we are evaluating the signals, we don't have other types of interference of other medical conditions that will give a signal that is not what we expected. So they are also assigned a protocol consent for being able to, so we can use their data. And we also establish an experimental protocol, and we are going to do, before doing the trial tests in the field, we are going to do physical tests in a laboratory, so in a controlled environment, where we are going to evaluate the performance of the firefighters and the rest and emotion. So this will enable us to evaluate the signal that we have in relation with movement. So this can be separated with other type of signals that we can be extracted and evaluate during the exercise. So we also will identify in the protocol other type of features that could interfere with the signal analysis. This means like tattoos, scars, hair body, that so we have to analyze all this, and ideally you should have some one or two individuals at least with these physical characteristics, also to evaluate what will be the impact of this in the signal that we are going to collect. So so all the other parameters will be collected with also with the ECG signal. And for the ECG signal analysis, we are going to evaluate the ECG signal. So this is a typical ECG signal which has different peaks: the P, the T, the R, the S, and T. So these peaks, their amplitudes, their variation, they give information. Not only about medical information, but also information that can be related with other emotional status like stress, anxiety, and other types of problems. So these, for analyzing this type of peaks, we are going to use some typical metrics used for the Bayesian analysis, which level 3, PCPI, heart rate variability. So these will be the standard metrics that we're going to be used for the data analysis that we're going to extract. And with this, we are going to identify the peaks and correlate it with the activity, and identify also movement artifacts that can be extracted from the signal and signal variability between individuals. So having large sets will allow us to have a better evaluation of the performance and a relationship, what could be extraction, how relationship, what could be usable and not. So to address the power challenge, this is something that it still exists. You know, batteries are necessary for all the wearables, and they need to be rechargeable, which for this specific case, our battery has, well, the wearables, they have low consumable energy, so they can last even months. But still they have to be changed, and they also pose some environmental hazard problems because they are disposable. In particular, this scenario, firefighters, they have an additional risks because they are exposed to very high temperatures, and batteries should not be exposed to more than 45 degrees because they can explode, they are deployable. So this is a problem that needs to be solved. So for this next trials, what we are going to do is do encapsulation to prevent this thermal encapsulation. But for alternatives, we are also working on other possibilities of using self-sustainable power supplies devices. So basically, we can, if we are thinking on wearables, so we can divide energy sources from two main groups. One is energy sources from the body, so extract body from body temperature, body movement, so biomechanical energy or biochemical. So this can be extracted through these type of devices like triboelectric, piezoelectric, thermoelectric devices that can be used as power sources. But you can also use devices that extract energy from the environment, and this means solar, photovoltaic, so radio frequency, energy harvesters, ultrasonic waves. So this is other type of wearable devices that can be used as power energy, which do not rely on, can substitute batteries in a more sustainable way. So among these sources, we have been working with triboelectric devices. So these are basically devices that are very simple to use. Any basically combination of materials can provide, because a triboelectric pair, because you basically need two different materials that when they are in touch, they can generate these electrostatic forces, and you can use them to produce some power. So the advantage of triboelectric materials is that they are very simple to fabricate, very cost effective. You can, anything, the skin, textiles, everything, wood can be used as a triboelectric material. So this is just a combination of materials to have the right combination, right material combination, and also you have different type of geometries which actually give an output that in terms of voltage is a very high voltage output. In terms of current is not so much, but it can be used as a power generation source. So we have been developing triboelectric devices for different applications, and because these type of devices, they depend, the signal that they produce, they depend on the area, on the contact movement, and also on other the frequency depth of the contact. They can also actually be used as biomechanical sensors. So we actually have developed fully band textile triboelectric devices, which is self-sustainable because you can use it to produce their own you don't need a battery to supply it. And they, based on their movement, you can extract and you can put it in different parts of the body, and with this you can relate different parts of movements of the body. So yeah, you have a movie here of how it works. So here you can see that when the arm moves, you can see the signal moving, and if the intensity of the movement increases, also the frequency will change of the signal. So you can use it both as energy source and also as a sensor. So another possible alternative for addressing this energy harvesting problem is using radio frequency energy harvesters. So ambient radio frequency, we are surrounding, so we are surrounded by communications, and these actually produce quite a lot of electronic noise, which can be used for energy harvesting. So antennas can be used also for communication, and sometimes a combination of energy harvesting and communication, flexible antennas, it's also a possibility for having an alternative fully embedded battery, like with a lower energy source. So another interesting thing about flexible textile antennas is that the textile itself can be used as a dielectric. So an antenna has, typically you have the backsliding part, you have an electrode, and then you have the dielectric. So here the textile can be a dielectric, and as you can see there, the different types of textiles have very different type of permittivity and dielectric permittivity, and these can also be used to tune not only the type of the antenna, but also the frequency of operation. So, so we have developed here, as an example, a wearable antenna that this is tuned for 5G operation 3.2, and so this completely wearable, and it was also completely built by fully printed processes. So also possible, also things that we have developed, which are not going to test still in the field test of Gestosa, is other types of fully embedded sensors. And one of them is humidity sensor. So we also have developed a fully printed, this is graphene-based humidity and temperature sensor that you here see this kind of discs has a very high humidity sensitivity and temperature sensitivity that we can, so we just have to have this disc and then the part of the electronic, which is thing that we are not so expert on that part, but we can embed, fully embed textile, other type of sensors in textiles. So futures challenge to wrap up. So one of them is when we are starting to collecting these data sets, and ideally having even more data sets of is to how to the very large data set analysis. Also communication protocols. I have not really talked much about that, but as I mentioned, there was this part of the communication, the distance is a problem, and with firefighters, they many times they operate in places where you don't have Wi-Fi, you don't have communication or radio frequency communication because they are these in black areas for communication, and they also many times they operate in their own specific communication channels. You have all heard about CRS, so this is something that we have not addressed here in this project, that is, we are aware that it's important to solve. And we are also think it's important to add other environmental sensors, like for gas monitoring, we only have body temperature, but we also be important to have environmental temperature sensors, other type of sensors, medical sensors for assisting other type of possibilities that we need to evaluate when we are doing to evaluate the team. So these are also things that we would like also to in the future to use, but in fully embedded devices that can be really wearable in these conditions, because like you said, like I mentioned, it's very challenging. So you all know what INESC is, so maybe you don't know what INESC does, so I will, if you are all more than welcome to visit us and to know not only what I do and other things that I do, but also what other people do. And I will finalize. Thank you for your attention.
We would now, we would now have a small question and answer session in case anybody has any doubt. I also post this to the people watching remotely. Does anyone want to ask any questions?
I actually brought a t-shirt if you want to see it.
I wanted to select the, I do have a question myself.
Yes.
So basically, these wearables are hardware to an extent, and they are providing the data that will help the firefighters and the other first responders with questions like situational awareness.
Yes.
Is there a software element that is part of the Safefire project meant to analyze this data and provide actionable steps to decision support, for example?
No, we are talking about an FCT project, which is 250,000 euros for 5 partners. So, I mean, there was limits. We did apply to a very large project in the European call, where we wanted to do this software, this platform for not only with wearables, but other type of surveillance like drones for evaluating the temperature around
The
parts,
affected area?
the affected area to see so the firefighters could attack specifically this area, other types of things that were also considered, but we were not granted. But yes, it's important to have that, but I think we need to start having also some data to know how to also to do this software, because not having this correlation of what data we can extract, I think it's also difficult to make a software without this data.
Thank you very much.
Yes.
Yeah, I have a question. So you were mentioning some things that could put in risk measurement. Is the sweat a factor of?
This is something that we are going. I mean, for the electrocardiogram, actually, it's better because usually it helps to adhere the garment to the skin, and this is important to have a good quality signal. Because otherwise you have to do, signal processing to take in consideration not only the movements but also this detachment, and to know what is a signal that corresponds to an event, a real event, or it has an artifact. So this is something that we also need to evaluate. But for electrocardiogram, for instance, it's actually good to have sweat because it improves the signal. Other types of signals we don't have in this specific project, but for instance for the SOC, where it uses electrodermal activity, there is actually having sweat is what you are measuring, because if you have more quantities of sweat, then you can relate it with, for instance, stress and anxiety. So, but this is all the type of analysis, but for these specific sensors that we are addressing, sweat should not be a problem.
Okay, so my other question would be, so going beyond the prototype, what would you see as the main challenges if you want to come to a product and scale up these kind of sensors and the adoption by the industry?
Yeah, I think after having data and some software, even like it is now, because like I mentioned, the t-shirt is already certified, and if you can prove the efficiency and the company already showed it last month in this textile show, Mob Textile in the north of the country, and they were already talking that you should involve da Autoridade Nacional de Proteção Civil to collaborate already with them to whatever we do it in coordination with all firefighters. So this is something, this is political, but is also necessary. So whatever we are developing is in accordance with the needs, the real needs of these teams, and taking into consideration what can be done in the field, and also in articulation with the authorities, so they can also implement this knowledge in the response they have with the rescue teams. I here mentioned just the firefighters, but for instance the t-shirt, the medical team in Coimbra, they are also medical workers, and they have already 3 prototypes which they are testing in INEM. Of course, we need to still evaluate the robustness of the solution, which will be. We have some already identified problems. One of them is that there is a lot of movement interference, so this probably either can be done by extracting the signal, taking into consideration the movements, or then having, because we also have this in vision, some other type of sensors that can some sort of attach better. So this is a dry electrodes, so we could eventually put some hydrogel sensors that would help this interface between the skin and the surface. Because typically, I mean, you have very strict regulation in terms of the garments that can be used, and they have to follow. And firefighters, they don't like very tight garments. So if you use some very tight garments, this could be a problem. We did not put it in this project, however, the sock could be a potential solution because there are some of the specific technical conditions that are mandatory for instance, for the sweaters. They are not for the socks. Socks can be normal, and they don't have all these technical requirements that you have in the t-shirt. But you, and you can put other sensors, not only the ADA, but for instance the PPG, which also can give you the heart rate variability. So we also discussing this with the company that could also be some potential route. But I think for the last discussion that we had, which was only last week, she said that we need to involve INCP and to have a better clear of what will be the best route to follow.
We also have a question by Fernando, which is online.
Can you hear me?
Yes.
So I haven't really heard everything that's been said. So maybe I will ask a question that we could have been in the press, but I'm sorry. Anyway, I have a set of questions. First one is this considered or was it considered or do you consider these technologies? Meaning, can it be used in Bluetooth?
This is Bluetooth.
I'm sorry, Fernando, we can barely hear you. It seems that we're having some issues with...
But I understood. You are talking about Bluetooth communication. If we consider, uses Bluetooth communication. That's how it communicates with the mobile phone. The problem is that Bluetooth has a very short range. And if you want to have communication with, for instance, the command operation of the firefighter team with the firefighters that are in the terrain, they can be 300 meters away. This is a problem. Another problem is that when they are inside buildings, Bluetooth does not give you the Y direction. So if they are attacking a fire inside the building, you don't know in which floor it is the firefighter. So this can also be a problem if you want to evacuate one of the floors, or if you want to evaluate exactly what is the disposition of the team. So this Bluetooth is not a problem. I would say that probably for communication, LoRa, it will be a solution, but I'm not a communication expert, so this is what other colleagues talk about when we are talking about us. But I know this communication is an issue. But again, rescue teams, they have their own channels, communication channels, and whatever solution that we do, we have to be articulated with attitudes in the terrain.
We also have another question by Pedro Mendoza, which is also in remote.
Yes, I can hear you.
I don't know the number of the slide, but in the beginning when you show the video, I believe it was in the end.
With the sock?
And my question is that a CPG sensor or plastic sensor instead of PCG?
There it was actually EDA, and then you have a accelerometer, but you also had a prototype with the PPG and the ADA to measure the heart rate variability and also the oxygen, the blood oxygen concentration. In that, but that was not used here in Safefire. That was for another project. I was just showing it for other wearables that we have developed, and that was for actually measuring, for monitoring epilepsy, but we are also now using it for measuring mental illness problems. And the issue with why using a sock, well, to start because our also involved a textile company that was expert in socks, and because of for mental illness, and it also gives us the possibility using in the foot that it's not so exposed to body movements like we have in the upper part of the body, because we do arms, and this has much more mechanical interference in the electrical signal, which we don't have in the sock, so the signal has a higher quality. But we have, for instance, we cannot put an ECG sensor because you need the right and the left part of the body to measure it, and the sock we can only, I mean, other unless we use these collants, how do you say this? Well, there you have the left tights, then you have the left and the right part of the body, but we use the ADA signal, which, I mean, gives us about other type of information that could also be extracted from the ECG, and we can combine it with the PPG, which is the signal actually in the ankle of the foot. It's also high quality. It's actually better quality than in the toes.
Another question that I have is about the signal processing. I don't remember the metrics that you mentioned, but my question is, do you use only time domain metrics or also frequency and non-linear metrics?
Also frequency and linear movement ones. But I'm not the expert on signal processing, but yes, they also use variability and these kind of metrics. Okay.
I don't see any more hands up, so I would like to thank you on behalf of the whole of INOV, and now I think it would be a good time to give the